We'll have a little bit of a different taste to the preceding one, so let me dive straight into the setup, which is, okay, very simply, we will be considering the story of quantum systems characterized by energies in contact with Bob system with its own set of energies. And the evolution will be in contact with a thermal equilibrium, which in principle is described, as has been already mentioned today by Fernando, by Gibbs state. And, well, I think that I will not have such an easy way to access the pointer, so let's do it like this. Very good. So here you have the description of the Gibbs state, which you can think of pictorially as the system in contact with the environment. Oh, okay, that's curious. The description that I will be using throughout the talk as a backdrop is quite agnostic with respect to the model behind it. That is the thermal operations, which is simply evolution of the system together with the bath in a closed way such that the interaction is energy preserving. This kind of interaction has two fundamentally important properties for us, which is Gibbs preserving. It maintains the thermal equilibrium once it's reached, and it's time covariant, so it doesn't matter whether we first apply thermal operations then evolve the system or the other way around. And in what follows, for most part, the restriction will be to energy incoherent states, which means that we can think about them in terms of populations. This allows, at least in the single system story, to think about majorization as governing the state transitions, which is simply stating that P can go into Q if its cumulative populations are fully above the target state, and has simple counterpart for the finite temperatures in form of thermomajorization, which can be thought of also fully geometrically in terms of probability or population simplex. With this little introduction to the tools, we can go to the first part based on work with Rafał Bistronie on local thermal operations and classical communications. And instead of giving expressions, we will think about it quite pictorially. That is with Alice, first measuring her system, and importantly, in order to keep on average the thermal equilibrium, the measurement needs to be energy incoherent, and the results of which are forwarded to Bob, who happens to be a bunny with access to thermal operations. Now, importantly, if we do not want to become Maxwell's demon, we need to erase the memory, while Alice is allowed to perform her own local thermal operations for post-processing. And the process begins in rounds, which essentially allows us to introduce classical communications between the parties. Now, thanks to the construction of the protocol, the Bob's operations, or in turn the subsequent turns of Alice, can be neatly compactified into an order 3 stochastic tensors, which have their symmetric variants. So if you think about bistochastic matrices, this is the order 3 equivalent of it. Within our work, we derive thermomajorization based outer bounds on state achievability. And now again, thinking purely in terms of pictorial descriptions rather than complicated expressions, we have the input states P and Q on Alice and Bob's side, respectively. The achievable states are described as the convex hull of the images of extreme operations that are available to us, while the outer bounds are just slightly larger than the actual achievable set of population. Perhaps the more interesting, and this is where we slightly depart from a population-only picture, is the story of thermally restricted Bell non-locality, where for Alice and Bob, we allow them to share a Bell pair or multiple copies of it. And now you will see the standard CHSH scenario where the observable is quite recognizable, and the two bounds, namely the classical one and the fully quantum one, are something that we should be familiar with. On the other hand, if we are restricting the whole protocol to follow the LTOCC, The multi-copy is bound by something in between, depending on the number of degenerate or non-degenerate levels in the copies. Most importantly, perhaps, as long as the single copy does not have itself degenerate levels, the detection of entanglement via LTOCC is impossible and asymptotically approaches the Tyrrellson bound. Intuition is kind of simple. Thermal operations are quite peculiar model within which fully unitary evolution is allowed whenever we have degenerate subspace. Therefore, by appropriately controlling separate energy degenerate subspaces, within each of them we can achieve full Tyrrellson bound, while the non-degenerate subspaces that are left over, well, they remain classical. Now the saturation of the bound and the speed with which we approach it depends on the number of levels, and the exact behavior depends also whether the gaps are rationally independent or of equal spacing with different cases in between. This was a short story of local thermal operations and classical communications, and I switch gears very quickly with operational advantages for thermal resource engines. And with this, Karol already mentioned a little bit on resources, while I will need to introduce you with how we think rigorously and model agnostic about resource theories. There are three basic ingredients to any resource theory, namely, we start with free states, which are a subset of the entire space of states. The free operations, which are defined such that the image of the free states under free operations is a subset of the free states. We are not generating any additional resources for free. And usually the theory is supplemented by a monotone, which is called a monotone because it is always reduced under free operations. As a simple example, thermodynamics under thermal operations that I already mentioned can be described first by free states, which is trivially just a single state, the Gibbs state. The free operations in this case are not uniquely defined. There are many models, but in our case we are selecting thermal operations which satisfy the condition of image of the free states, that is Gibbs state, is still a Gibbs state, and exemplary monotone can be given by free energy, which reduces as we close to the equilibrium. Now, resource theoretical perspective of engines has been introduced first by Wojewódka Ściążko, Puchała, and Korzekwa, and we with Rafał Bistron tried to further formalize the setting. So with a single bath, at best you can just thermalize as you can see above. However, as soon as we introduce another bath, when we are thinking about thermal engines, we are able to construct useful machines, coolers, thermal engines, and extract benefits out of them, which are not necessarily monotones under either of the theories, which may not be thermal theory, but a pair of resource theories giving what we refer to as engine theory, with its own free states, which necessarily are larger than the individual free sets of the underlying theories, its own free operations constructed from underlying free operations, and maybe monotones. Who knows? Now, these are mostly formal results that are useful in terms of assumptions about what constitutes the free operations. It is enough to consider strokes that are subsequent, and that each stroke we are using only extreme operations of the underlying resource theories, and the full set of free engine operations is simply the convex closure of such set, with the simple consequence whenever free states are convex as well, that the full free states of the engine is just an image of the extreme points of the free engine operations on the extreme points, not just simply of the free states of the engine, but of the underlying resource theories. Now we would like to introduce at least some way to quantify advantage with respect to benefits which may or may not be monotones of the underlying resource theory. One sensible candidate is the relative advantage, which quantifies how much more benefit we are getting from an input state with respect to engine operation before and after, or free advantage, which quantifies for us something slightly different, how much more benefit we are getting with respect to the original free states. Okay, so these provide quantitative information about how much advantage we are getting. Now, very quickly, I will just mention that one of them, if fed with monotone, is actually creating the monotone for engine resource theory. And one can construct an engine efficiency, which in steps is very similar to how the benefit is constructed with respect to free states of the engine theory. This, interestingly, turns out also to be a faithful monotone. That is, it is 0 for any free state of the engine. Now, very quickly, because I apparently am slowly running out of time and in the interest of our lunch, we will consider pictorially 3 benefit functions: ground state population, excited state population, and negativity of entanglement, which is obtained assuming that at the last step we have common control over 2 qubits. Pictorially, you can think about it like this for 2-qubit non-engines, which are in equilibrium with either hot or cold. We choose it locally, and this is simply our backdrop and the comparison point. As soon as we allow each party to work with the actual engine, you can see that the set of non-entangled states gets way smaller with the direction of very low temperatures, that is exponential of beta going to 1, is actually almost maximal. Changing it over to allowing both parties to communicate even in a classical manner further expands our ability to generate entanglement. On the sides, you can also see what are the advantages for populations on the ground in excited state. And the most important feature is that in this case, the maximal entanglement is actually generated both for very high and very low temperatures for both parties. And the last little quick thing is what happens when we allow full thermal operations over both qubits to be accessible in each stroke, which turns out to generate some critical temperatures which are interestingly connected to inverse golden ratio, inverse silver ratio, and just 1/2. This was quite a quick segue through the advantages and benefits that one can achieve with resource engines when restricted to thermal resources. And one sentence summary, which I would like to advertise the frameworks themselves. First of all, LTOCC is allowing for considering the distributed thermal operations scenarios, such as, for instance, thermally restricted Bell inequalities, or in the future multipartite versions of it. And resource engines generalize the stroke-based idea of thermal engines and allows investigation of how benefit functions are enhanced under the operation of the engine. What did I skip? Quite a lot, and I will not be reading through all those. And you will be able to see all those results in the papers. And in the interest of time, I am closing down a little faster. Thank you very much for your attention, and I'll welcome questions.
Great. Thank you very much, Jakub. Questions, please. We have the Joker, but first at the back.
That's good.
There is something I'm curious about resource theory. So between 2 qubits, you can have classical correlations or quantum correlations. Let's use discord as a measure. How does discord affect your formulation in your approach?
So this is a little bit of a challenging story because thermal operations at the very least are very hard to describe as soon as you introduce correlations. I am aware of one asymptotic results about transformations between coherent states due to, I believe, Shiraishi and Takagi. And beyond that, so far it's been hard to apply these theories to coherent states. Nevertheless, the result has appeared in between us submitting the LTOCC and publication. Therefore, we have not attempted to use it for the results. Maybe it's applicable, maybe not. I hope that answers your question.
Other quick questions? Federico, please.
I don't understand completely the Bell scenario.
Okay.
In a Bell scenario, I expect mutually unbiased bases, and I don't know how to apply this to thermal operations. And also, I don't understand what is a violation ruling out in this context.
Okay, fair. So this is something that I under-explained in a certain sense. Think about it as Alice and Bob holding several copies of 2-qubit Bell state, okay? But they are restricted to energy incoherent measurements and unitary rotations that are still energy preserving. This means that they are able to implement what you are mentioning, mutually unbiased bases, but only within these specific subspaces. This is how you're getting the non-degenerate subspaces still remaining at the classical bound, while within each, say, direct sum of the degenerate subspaces, you have separate pairs of mutually unbiased bases that allow you to saturate the Trilson bound for all of those. Does it clarify a little bit?
Yes. Still, what is a violation ruling out? Like the same local hidden variable description, I guess.
Yes, we are thinking still about local hidden variable descriptions exactly in the same vein as the old Bell scenario. The only difference is that instead of allowing arbitrary measurements on Alice and Bob, we are restricting all the pre-preparation and measurement to LTOCC scenario.
Okay, thank you.
Was that the final question? It appears so. Thank you. Let's thank Jakub again.
Thank you very much.